Welcome to this presentation on classical geometric construction of whole number encores in general. My name is Kimuya Alex from Meru University of Science and Technology, and this is an image of me. This presentation is featuring on three key contents and the Alex Kimuya theorem of classical geometry in the domain of classical construction of whole number encores and the encore trisection problem. I am really excited to talk to you about some very new ingenious discoveries in geometry based on the capabilities of the traditional Greek tools of geometry. Before we get started, here's the general agenda for this presentation. I will start with classical construction of all the whole number encores in general. I'll then talk about the classical geometric partitioning of a particular encore into a certain ratio. And lastly, I'll address on the application of Alex's theorem or method in the construction of the infinitely many regular polygons. This series of presentations is structured as follows. I'm going to cover on three modules organized with respect to the stated three general objectives. The first module is a series of videos demonstrating on the classical geometric construction of all the whole number encores, their multiples and submultiples. The second module is a series of videos addressing on two concepts, the geometric partitioning of an encore into a certain fraction, and number two, the general proof that it is geometrically possible to construct all the whole number encores as well as the slicing of an encore into some fraction. To begin with, let me point out that the problem of classical geometric construction of all the whole number encores in general is an odd age problem in classical geometry. It can be classified together with the problems of the encore trisection, cube duplication, also called the Dylan problem, and the problem of squaring a circle. In most cases, the problem of construction of all the whole number encores is mistakenly interpreted as the encore trisection problem. However, according to these two papers, the possibility of encore trisection and short review on classical construction of all the whole number encores and the encore trisection problem, though both problems are classified as plain geometric problems, the encore trisection problem is purely a different problem from that of the classical geometric construction of all the whole number encores. By definitions, 1. The encore trisection problem asks that, given an arbitrary encore, generate an algorithm that will geometrically divide the given encore into three equal portions. In such cases, the size of the given encore does not matter. On the other hand, we can construct the classical geometric construction of all the whole number encores problem as, given the traditional or the classical straightedge and compass, create a method that would help resolve the geometric construction of all the whole number encores, their multiples and submultiples. Having known the difference between the two problems, under this presentation, I'll confine myself on those constructions involving the geometric construction of all the whole number encores and the trisection of a particular encore. As such, I'm going to show how to trisect encores of magnitudes 21 degrees, 24 degrees, 36 degrees, 48 degrees, 54 degrees, 57 degrees, 60 degrees, 72 degrees, and so on. Clearly, majority of humans are familiar with those constructions involving only the encores multiples of 15. As such, we are able to construct encores of magnitudes 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees, in that order. A construction of another type of a whole number encore has remained a mystery until the creation of Alex's theorem in the possibility of the encore trisection in 2017. In his theorem, Alex discovered some elemental objects, that is, some line segments, in the domain of a circular plane, which when employed in a construction with the help of the Compass-Straightedge theorem, one is able to construct all the whole number encores, as well as the trisection of the infinitely many trisectible encores. In his proof, Alex used encores of magnitudes 48 and 60 to justify his hypothesis. Therefore, this presentation is aimed at demonstrating the Alex's Compass-Straightedge work using an interactive computer software. Clearly, a high-profile contemporaries have closed the door in solving the mentioned classical geometric problems of antiquity by assuming them impossible for Compass-Straightedge construction. For instance, Pierre Wansel of 1837 published an ambiguous algebraic proof based on ideas from Galois field of numbers, showing that the solution to the N-core trisection problem corresponds to the solution of the cubic equation x cubed minus 3x minus 1 equal to 0, which is stated as an irreducible equation. Wansel considered that since the time scientists and mathematicians were not able to geometrically construct all the whole-length N-cores, it was then impossible to trisect an N-core of magnitude 60 degrees, simply because people are not able or have not been able to construct an N-core of magnitude 20 based on the stated restrictions of classical geometric constructions. In his proof, Wansel's theory begins by giving a series of quadratic equations showing that all the classical geometric problems can algebraically be proven to be correct. However, the contradictory aspect in Wansel's proof of the N-core trisection possibility is that he advanced in the use of cubic equations to show that the N-core trisection problem solution would always correspond to solving this cubic equation, which cannot be solved using a compass and a straightedge. But according to the early mathematicians, and here I'll not go deeper into the literature, I'll quote the paper by Descartes published in 1637 and again in revised form or version in 1664. He says that any form of a geometric solution involving both the quadratic equations and the cubic equations, it is not a classical geometric solution, but rather a solid geometric solution. From this point, we begin to see the limitations of the Wansel's or in the Wansel's algebraic proof of the N-core trisection possibility, in the sense that 1. It turned the N-core trisection problem into purely an algebraic problem or a solid geometric problem from its classification as a classical geometric problem. Number 2, Wansel's proof again does not obey the classical geometric constructions, which include number 1, the first condition or restriction of the classical geometric constructions is all the classical geometric problems should be solved using only two tools, that's the compass and the straightedge. The mentioning of the straightedge here is very contentious in the sense that the modern ruler we use has markings on it, and this kind of straightedge did not have markings on them. What this means is we are completely prohibited from doing any form of measurement in the constructions or when performing a construction. Measurements are completely prohibited or forbidden. Number 2, any form of a construction procedure should not involve arithmetics. To bring the discussion in under this condition, we have to here we are going to consider two points. 1, we consider the relation between the 20 degrees angle and the 60 degrees angle. The 60 degree angle is an angle of a specific value which is constructible. It's an unknown angle, and again 20 degrees size of an angle has not been constructed before, and Wansel was not able to construct it himself. So what that means is, for us to trisect an angle, we need to understand the fraction of the angle to be constructed. That's purely arithmetic. And though it can be a geometrical arithmetic, as I'll be showing in my constructions, that's again not allowed when solving the trisection of an arbitral angle. As I've defined, an arbitral angle is that angle whose value or magnitude is not known, and again it should not be measured. So the use of 20 degrees and the 60 degrees angle shows the misconception Wansel had as far as the angle trisection problem is concerned. It would be very clear if Wansel again used two specific angles and say that we cannot have a method that can help divide these two angles, such as an angle of magnitude 60 and 75, into 3 co-portions each without altering the construction. That could have made much sense than saying, since we cannot trisect 60, it's impossible to trisect all the encores. Since we cannot construct 20, we cannot trisect 60. That shows the one cell's proof did not take into consideration that the encore trisection problem was based on an arbitral encore, an encore of any value, whether a whole number encore, an encore that is not a whole number encore, an angle that's a multiple of 15 degrees, and all those other angles not multiples of 15. Number 2, we consider the trigonometric approach in the one cell's proof of the encore trisection possibility. We are not allowed to do some arithmetic again, and trigonometry is not geometry. So simply that consideration shows one cell did not give respect to the classical geometric language. We should not depend on trigonometry in any way if at all we are solving the encore trisection problem, and if at all we want to aim at solving the construction of all the whole number encores. They are all classical geometric constructions or problems, and they need to work under these specified conditions. Again, one cell did overlook the fact that Euclid himself in his classical works did not use the modern number systems, even in his proofs. Euclid worked with proportions. The only type of numbers allowed were the unity, that's 1, 2, 3, up to 9. The number 0 and negative numbers were not accepted. These numbers again represented magnitudes. Euclid in several accounts of his proofs are seen in the first 4 books of the Euclid Elements. He used the term commensurate, which means equality between quantities of a similar kind, and this shows the aspect of comparison. Now, encores also form a kind of a magnitude, and one cell's proof of the encore trisection possibility did not take such a consideration into account. Number 3, another condition is the construction procedure should have a finite number of construction steps. When you talk of the cubic equation x cubed minus 3x minus 1 equal to 0 as an irreducible equation, it simply means we cannot have a classical geometric procedure aimed at a solution to the encore trisection problem with a terminating number of construction steps or with a finite number of construction steps. That's again a very, very wrong perception of algebra to a classical geometric problem. And number 4, the other condition is there should be no transfer of distances in the construction procedure. This condition could mean 2 things. Yes, we are not allowed to transfer distances, but again, we can at some point use measurements and transfer the distance in terms of measurements. So it's a bit a condition, yes, under classical geometry, but it's not one of such a serious condition or a fashionable condition to deny people the transfer of distances. For instance, we find the concept of transfer of distances in many applications. We consider the construction of some regular polygons such as pentagon, hexagon, and so many other constructible regular polygons. Those kind of constructions are multi-step procedural constructions. They are not direct constructions such as bisections, and they would definitely involve transfer of distances. With the help of the compass equivalence theorem, when one does the transfer of the distance of a distance of any distance, that is an arbitral distance, that does not violate any classical geometric construction because we already use it, we already employ it in solving some problems. So, in the following videos, or in the videos I'll be showing how to construct all the whole number encores, their multiples and some multiples and some other problems, so how to solve some other problems. We'll be working with it, some transfer of some distances we are going to generate to help us accomplish those tasks, and will greatly depend on the compass equivalence theorem to give us that freedom to transfer the distances. It is now geometrically clear to say that one cell's proof of the assertion that the solution of the encore trisection problem corresponds to the solution of the cubic equation x cubed minus 3x minus 1 equal to 0 has no geometric validity, and it's not one of the best proofs to be considered as a geometrical proof. I would also like to point out that the most difficult task for us as humans to prove in the world of science is to prove an impossibility. There's a big difference between the terms impossibility and inability. Being unable to solve a particular problem for a couple of years does not mean it's an impossible problem. Those are two different terms or considerations. In a totally different presentation, I'll expose some demos or some demo on the angle trisection solution. I've written a paper on the solution to the angle trisection problem, and it provides or it presents one of the most elegant solutions. The shortest number of steps that can be done on a piece of paper using a compass, straightedge, and a pencil. Back to this presentation. To prove the claim that it's geometrically possible to solve the problems of the classical geometric construction of all the whole number angles in general, and the partitioning of a particular angle intersection ratio, we would greatly depend on these two papers. The possibility of angle trisection, which gives or provides a Compass-Straightedge construction, and the other paper is on short review on classical construction of whole number angles and the angle trisection problem. To open this paper, it's published by the Journal of Mathematics and Systems Science. It's housed by the David Publishing Company in the United States. This is one of the very interesting papers, and we'll extract a lot of content from this paper. There are some theorems and some very interesting results. You can see the use of GeoGebra or the software GeoGebra in activity for results visualization. It's one of the interesting articles. It's an open access paper, and you can find a copy of yourself from the internet. This other paper is attached in the academia site or the community, also freely available in the internet. Download a copy of yourself. Now, in the videos I'll showing how to construct all the whole number angles, we are going to encounter results of this kind. We learn how to construct angles of magnitudes 20 degrees, 10 degrees, using the classical tools of geometry, that's the compass and straightedge. We'll learn how to construct an angle of magnitude 1 degree, 2 degrees, and simply, if you're able to construct 1 and 2, then we should be able to construct all the other whole number angles, the multiples and submultiples. Simple as that. But again, that does not mean we have solved the angle trisection problem. That's a very different problem from this one. We'll learn how to construct angles such as 8 degrees, 9 degrees. Very interesting results here. We will learn how to trisect angles, as I've said, from maybe 21 or another trisectible angle, provided you can generate it geometrically. You can construct 7, 14, and so many interesting angles. Looking at this figure, we have 3 types of circles inside. There are 2 circles in a black, sharing a common center A. And again, there's another circle here in green. If you have come across the use of the compass equivalence theorem, we can see it in application. This is the radius Ji equal to the radius Ia, where Ia equals to what? It corresponds to B prime A, and B prime A is the same as AB. Since B here is an image, B prime here is an image of B under some geometrical reflection or transformations. So when I will be demonstrating the proofs to these problems, I'll show how the use of compass equivalence theorem is very helpful in generating of a geometrical proof, not an algebraic proof. Neither will I use trigonometry. No. We are also going to learn how to construct some polygons of interesting size or ratios, such 10-sided polygon. It subtends an angle of 36 degrees at the center, and we call that a decagon. We'll learn how to construct it, and so many other angles such as a nonagon, pentadecagon, and so on. And lastly, to help us understand this new piece of knowledge, I'll use the GeoGebra software in my demos. GeoGebra is an open source dynamic mathematics software for teaching and learning mathematics and mathematical sciences or engineering sciences with the simplest applications, from middle schools through university level. It is as easy to use as a dynamic software, but also provides some basic features for all of computer algebra system to bridge some gaps between geometry, algebra, and calculus. What I've just opened here is the GeoGebra software. We have this window called the Algebra View window, and this is the graphics, the 2D graphics window. On this bar here, or the toolbar, we have several toolboxes containing some tools. For example, if I need to use a point to do some labeling, I'll just pick that. I could also be interested in using some straight lines, maybe a straight line complete one, a line segment, array, some vectors and such. I can use that toolbox to provide me with the tools. I would need to do some parallel lines, some perpendicular lines, perpendicular bisectors, some anchor bisectors, perpendicular bisectors, tangents, tangents, and so on. I also depend on this other toolbox to provide me with a compass tool, which is also very essential in the constructions. There's also another tool here for results visualization. I need to do some measurements to be sure or to ascertain if the claimed construction gives the said results. Again, we do some geometrical transformations from this toolbox. Can reflect a point about another point, as I've shown in the previous figure, point B being mapped into point B prime about point A. And we'll do some magnifications for clarity, for good view of the results. So we do some magnifications using some tools in this toolbox. You can zoom in your figure or zoom out your figure, depending on what you want to show or to see or to figure out from your constructions or diagrams. Before I conclude, I would like to point out something here. I have plotted maybe 3 points in this figure. From the algebra view window, point A's or points A to C, they come with their coordinates or their locations in this plane. In my constructions, I'm not going to depend on these coordinates. I'm not interested in using these coordinates either in the proofs or in the constructions. Purely classical compass constructions. What I'm going to work out is a mimic, or I'm going to mimic the use of the pencil, the compass, and straightedge on a piece of plain paper to do my constructions. I will not do measurements. I will not use things like all features such as these sliders and so on. No, I'm not interested in that. But just the point A, B, C, or D. Having these 2 points, then I can do my construction. It will be as simple as that. Now there are so many other features in this software. You can one can use the CAS. It has the built-in CAS. You can raise the 3D graphics as this and perform your constructions and so many other things. I'm not going to the 3-dimensional. What I mean by 3D or 2D is 2D stands for the dimensions. So I'm not going to 3 dimensions, but into 2-dimensional constructions. And sorry, what am I doing? That is the end of this demo. Thank you for viewing. Please take your time and go through the other videos addressing on the constructions of some particular anchors and some other types of constructions besides just the anchors. Once again, thank you very much. Remember to subscribe for this presentation.